3.10, or as Juan would have it, 3.1. So are those, is that not a significant digit? Is that how that works? Because it's increasing the accuracy. You're saying we know what, yeah, okay, so. All right. Well, the interesting thing is on the website, in order to get these to order the right way, I have to put a Z in front of the file name for this, because all it is just a file cabinet. I just put them in there and then it orders them. So this section is on linear approximations and differentials, which hopefully isn't too terribly hard. It is one heck of a lot easier than the stuff we've been doing for the last couple of days, the related rates. And hopefully as easy as it is, and we're going to build on some ideas that we've already talked about, it has some really cool applications and the beginning of some ideas that you'll use when you take Calc 2. So we'll go with the starter question here. It says, how do we like to write point slope form of a linear equation in this class? So if we just wrote point slope form, y minus y1 equals mx minus x1, what we normally did is we normally moved that y over to the other side. So I'm going to write this as y equals, I'll have y1 here, and then plus m, and then x minus x1. So if we moved that y over to the other side, I could then plug it into the calculator. And I don't really have to do any extra work, any combining of fractions or anything like that. Okay. Part B says, in calculus, what word is nearly interchangeable with slope? Derivative. Okay. So if this is point slope form, it's got a slope in it, and we're in a calculus class, what could we replace that slope with? We could replace it with a derivative, a y prime or an f prime or something like that. But it would have to be the correct slope at the correct point. So I'm going to write this as y equals y1, and then this is going to be f prime at what particular point? At x1, at that particular x value. Okay? So that would be another way to write point slope form. Okay? Easy enough? Okay, and I think we've actually talked about this idea before. I think we've written something very similar to this as we've gone through chapter 3. Okay, so the next thing we're going to do, we're just going to look at example 1, and we're going to pick up on an idea that we've done several times. It says, find an equation of the tangent line of y equals x squared at x equals 1. Well, we need a couple of things in order to do that. So I need y prime. Okay, that's going to be 2x. That'll give me the slope, and I'm going to evaluate that at x equals 1. So that would tell me that the slope is 2. And I need the point. If I plug in a 1, I get out a 1. So this is going to be y equals, if I follow this pattern right here, the y coordinate is 1, and then plus the slope is 2, and then it's going to be x minus the x coordinate is 1. So this is what we're going to type into the calculator. Okay? So let me pull that up. Okay, so we're going to type in the original function, y equals x squared, and then I'm going to type this in. So this is 1 plus 2 parentheses x minus 1, close the parentheses. And I'm going to hit zoom 4 for the decimal window. And we should see, there it is right there. So there's our tangent line. We've seen this before, right? And then it says, let's zoom in at the point of tangency. So I'm going to go over to 1 and up to positive 1. That's going to be the center of my zoom. Kind of works like Google Maps or something, like double clicking at a place on the map. So I'm going to hit enter. Okay, there's the parabola. There's our tangent line. Okay, notice the point is still 1, 1, so I'm right at the point of tangency. I'm going to hit enter again. And if I continue doing this, I'm going to do this one more time and take a good close look. This is going to graph the parabola. Okay, then it's going to graph the tangent line. There's the parabola. Okay, did you see anything change? Okay, barely, right? And if I hit it one more time, there's the parabola. Take a good look. What happened here? What's the only difference between the graph in this window, between the graph of the parabola and the graph of the tangent line. What did it do? Did you see what it did? Is it large enough that you could see? I'll do it one more time. Take a look at just focus at the very top. Focus right up here. Watch. You can see one at the very bottom. It adds one extra little pixel there, right? Okay, now if you were to look at this, if somebody walked in this room right now and they said, hey, what shape is the graph on the screen? What would they say? They'd say it's a line, right? Okay. Even though clearly we're dealing with a parabola, it's got a pretty good curve to it at this point. Okay. If I looked at the window, this window is, so we're maybe, what are we, about 1,000th wide and 1,000th tall, somewhere in that neighborhood. Okay. It looks essentially like the line. Okay. So this is kind of the point of this whole section. Okay. If you zoom in at one point on a smooth curve, okay, no matter how curvy it is, so we're dealing with like polynomials or trig functions or something like that. No matter how curvy it is, if you zoom in enough, it's going to start to look like a line. In fact, it looks like what line? Looks like the tangent line. Okay, not just any line, but the tangent line. Okay, and there are a couple of important points that we want to comment about right now. So it says the tangent line looks a lot like the original curve when we zoom in. Well, no duh, you've probably been doing this since you had a graphing calculator, right? Okay, but here's the more important part. The tangent line is a good approximation. It's a line that provides good approximation for the function values near the point of tangency. So one of the nice things about lines is they are extremely easy to work with. Regardless of what the slope is or what the y-intercept is, they're pretty darn easy to work with because they have such basic operations. You're basically talking about multiplication and addition. Okay? Very, very easy to work with. And yet we can use a tangent line to give us pretty good approximations for some curve. Okay? If we've got the tangent line, we can come up with approximations. Okay? All right, so like we saw up above, if we use point slope form, we can actually take that point slope form and put it a little bit more in terms of calculus terms. So if the point of interest is x equals a, so if we're interested in that being our point of tangency, then the point would be a comma f of a. So if the function is f, our x-coordinate is going to be a, our y-coordinate is going to be f of a. So we're kind of leaving this notation in the dust for just a second. Okay? The derivative at that particular point is going to be f prime at a. So if we were to plug this into normal point slope form, it would be y minus, what y value are we using here? We're using f of a. Okay? I need the slope. Slope is the derivative. Derivative at that particular point. So that would be f prime at a, and the x-coordinate is a. And then all I'm going to do from here to here is just rearrange it a little bit. I'm going to take that function value and put it over here. I'm going to have the slope, which is the derivative, in front of x minus a. And this right here would be a quick way to write down the tangent line for a curve at the point A. Okay, now what's nice about this is what determines our tangent line? How many things do we have to know? How many things do we have to plug in? Yeah, all you have to know is the point of interest. I mean, clearly you need the function that you're working with, okay? But if you know what a is, f of a goes right here, a goes right here, and f prime of a goes right there, and you're done. You've got the tangent line, okay? All right, so this is what we call, this book calls it a linear approximation of f at a. Some books call it a standard linearization. Okay, but this right here, this notation here, and notice all we've done is taken something that looks fairly familiar, and we just replaced that y with an L of x. So that means this is our linear approximation. So our L reminds us that this is a linear approximation, okay? So on example two, I've got 3 different problems here. The instructions for each one is the same. It says find a linear approximation for f at a, then graph f of x and L of x on your calculator. Okay, so this would be something that you definitely want to know how to do for a test. So here's what we're going to need. We need a, we need f of a, and we need f prime at a. Because to make the linearization, it's these guys right here. So I've got to have f of a, f prime of a, and a. We're given a, so let's go ahead and do this problem. Let's find the derivative. And what would I get? Is that a tough derivative? Derivative of the outside, leave the inside alone, times it by the derivative of the inside. What is the derivative? E to the x minus 2. It's the exact same function. Because the derivative of the inside would just be a 1, right? Everybody okay with that? Okay. We're sure? Okay, definitely know how to do that for a test. That would be a very easy derivative to find. Okay? Yeah. We're using e to the u. The derivative of e to the u would be e to the u du dx. So if u in this case is x minus 2, then du dx is 1. Okay? That work? Okay. So let's write the linearization. So the linearization would be L of x. Okay. I need f of a. I need f of 2. Plug in a 2. What do you get? E to the 2 minus 2. So e to the 0. So that's going to be 1. Plus, I need the derivative when I plug in a 2. Also 1. And then x minus 2. Okay. Okay. There is the standard linearization. There's our standard linearization. And then it says, let's see, graph f of x and L of x on the calculator. Now, the reason I like to leave it in that format, even though it doesn't look very good, it looks like, gosh, we could easily simplify this. All I need to do here is, let's put in the exponential function, x minus 2, close the parentheses. And then you'll notice that the format for all of these is exactly the same. You have a y value, and then depending on what the slope is, and how much we change x from whatever the original a value was, we're going to go up or down from there. So I need a 1 here, I need a 1 here, and then I have an x minus 2. Structure's the same. I just go in and edit the original function, edit 3 things here, function value, slope, and a. And I'm going to hit zoom 4, and let's take a look at what this looks like. Maybe this will be a decent window. We should see something right there, and there it is. Okay? Same situation every single time. Okay? We're going to see something that, we're going to see a line that is a good approximation for the curve. So let me grab this. Okay. All right, let's do this one here. Let's find f prime, cosine of x. I've got a. I need f of pi. So that's going to be the sine of pi, which is 0. Okay. Y coordinate pi. Y coordinate at pi is 0. Okay. And then I need f prime at pi. I need the cosine of pi. Cosine, that would be the x coordinate on the unit circle at pi at 180 degrees. So that's going to be -1. Okay. So that means my standard linearization is going to be function value, 0, plus the slope, which is going to be a -1, and then x minus pi. Let's see, I've got this in, I'm going to make sure this is in radian mode. Come back here. Let's see, sine of x. And think about what this is going to look like. Oops. And then I've got 0, -1, and then x minus pi. Pi is above the caret key there. So before you type something into your calculator, you ought to at least have a guess as to what it's going to do. We're talking about the sine curve. Sine starts at 0, goes up, hits 1, and then comes back down. So we're on the downward side when it goes through 0 at pi. Has a slope of -1. So I'm going to hit graph here. Pause it right there. We should see a line that goes through this point right here. And there it is. Okay. And you'll notice because it's kind of straight right here. Look how good an approximation this is. Okay. I mean, these overlap each other for quite a while, a lot longer than the other ones that we've done. Okay. All right. And would you do that last one there? Tried to pick nice functions, fairly easy values. That's it, right? Y coordinate 1, slope is 1/2, x minus the x coordinate. So we should see something, if we were to graph this, it's going to go through the point 1, 1, and it should look like that. We'll make that nice and fat so it's tangent. Okay? And if you throw that in your calculator, that's what it's going to look like, right? Okay, and again, what's happening here is, let's think about this for just a second. It's taking the old y coordinate, wherever our point of tangency is, and then based on how much we change x from 1, what the difference is between our x coordinate that we plug in and 1, it's varying the slope. Okay, so it's going to be 1/2. So if we go, 2 units away from 1, it would go up 1. So if I go over 2, I'd go up 1. Okay, and that would be a decent approximation, but a pretty good curve right here. So it doesn't hug next to it as long as maybe this one right here does. Any questions there? Sure? Okay, so let's take a look at the next topic, and this is where we get into approximating here. So it says, even though a line is about as simple a function as you can get, we can actually use those to make approximations that are pretty darn accurate. Okay? And the point here, and you'll do a bunch of this when you take Calc 2, sometimes finding an exact answer isn't possible. Or if it is possible, it would take you so much time and energy, it's not worth it, when a pretty good answer, one that's, maybe within a couple thousandths or something like that, is totally okay. It's within our tolerances. Okay? So these linear approximations are pretty darn useful for at least getting a sense and a flavor for how approximations would work. So here's what we're going to do. I realize you could type this one into your calculator, okay, and you could get the exact answer out to 10 decimal places or something like that. But that's not the point. What we want to do is we want to use a linearization, okay? We want to find some line, some linear function that will approximate square roots at a particular point, okay? So here's what we're going to do. If we're going to approximate square roots, what function should we use for our linearizations? Square root, okay? So f of x is going to be the square root of x. That's the function we're going to use. Now, when we say what is a good candidate for a, which we also call the center of the linearization, if I'm going to use a line to approximate the square root of 1.2, what that means is, what point would be pretty easy to plug into the square root function that's near 1.2? 1, okay? So we're going to use a 1. Because it's pretty darn close to that, and it's easy to compute. Okay? So find the linearization. Is this hard? Just did it. Thank you very much. And you have it on the same page, don't you? So this is going to be 1 plus 1/2 and then x minus 1. There's our linearization. It's the one that we found at the bottom of that previous page. Okay. Then it says get an estimate. Get an estimate. Now stop and think about this for just a second. Okay. If I want to, so here's what we're saying. We're saying that f of x is approximately equal to L of x. So f of 1.2, which would be the square root of 1.2, is going to be approximately equal to L of 1.2. So that should be 1 plus 1/2. And then what do I plug in here? I plug in a 1.2, just like it looks. Now, think about what I said just a second ago. What the slope is doing is it's figuring out, based on how much we varied from the center of the approximation, and if the center of the approximation is 1, and I'm computing a value at 1.2, how much did I vary from 1? What's the difference between the point I'm plugging in and 1? 0.2. That's how much I let it vary. And look, this does that computation for us. Okay, this is going to be 0.2. So we're going to take our old function value of 1, which would be the square root of 1, and we're going to add half of however much we varied from the center of our linearization. Does that make sense? Okay, so what's half of 0.2? 0.1. Pretty darn easy calculation. You don't even need a calculator, right? So we end up with 1.1, right? So let's string this all together. What we're saying is f of 1.2 is approximately 1.1, or in other words, the square root of 1.2 is, whoops, got this approximately in here, following from here. Okay, now throw that in your calculator. Okay, the square root of 1.2 is, I'll just pull it up here, square root of 1.2. 1.095. That is pretty darn close. Okay? Now, if we were to take that, and let's figure out how much we're off. What is the difference between the actual answer and our approximation? Because our approximation is 1.1. Let's compute that. So let's subtract 1.1. We're within tenths, hundredths, thousandths, 4/1000ths of the correct answer, just using a line. And when did we start using a calculator? Not till here. Okay, we got this answer. Whoops, we got this answer without a calculator, and it's within 4/1000ths of the right answer. 45/10,000ths of the correct answer. Okay, so pretty darn good approximation, right? Okay, Weston would take that to Vegas. Very nice. Okay, so you have some problems that ask you to do stuff like that and use those approximations. Okay, in Calc 2, you do stuff that's a little more sophisticated. You go away from just using lines to using maybe curves that will approximate other curves, but they do it in a pretty cool fashion. So now let's talk about kind of an issue that we've skirted around for just a little bit. We've broached this topic, and I've talked about differentials a little bit, but now we're ready to deal with them a little bit more formally, okay? So differentials are a lot like derivatives. You can kind of think of them as parts of derivatives. And the cool thing is the rules, there are no new rules for working with differentials. If you know the rules for finding derivatives, you automatically know the rules for finding differentials, okay? So the differential of y is plain old dy, and the differential of x is plain old dx, okay? And what it means is, literally, the difference in y and the difference in x, okay? So the rules for finding differentials are just like the rules for finding derivatives. It's just that we don't differentiate with any particular variable. So when we say with respect to x or something like that, okay, we kind of leave that part off here. So we don't differentiate with respect to any particular variable, okay? Well, the cool part about this is if you need to, you can decide what variable you're gonna differentiate with respect to later on. Or what we're gonna do in these examples right here is we're just gonna find the differential of each side. So this is the way this works. The differential of y is dy, and the differential of x is dx. It's literally that simple. If we happen to have a slightly more complicated function on this side right here, like y equals 2x, the differential of y is dy, and the differential of x is, think of the constant multiple rule. It's going to be 2 times the differential of x, which is dx. Okay, now, before we do the rest of these, I want to show you what this means. This would be the line y equals x, and this would be the line y equals 2x. Okay, this means for every change in x, I get exactly the same change in y. So this is dx, this is the difference in the x, this is the difference in the y's. Okay, if I have this one right here, if I have y equals 2x, the line is twice as steep. So if I have the same dx here as I have over here, how does dy compare to the dx? It's twice as big. Okay? So that differential has something to do with the slope. Okay? The change in y is going to be twice as big as the change in x. Okay? And if I have an even more complicated function that has a curve to it, the change in y is going to depend not only on what the change in x is, it's going to depend on how steep this is and what the slope is at different points. So watch what we get here. dy would equal derivative of the outside, leave the inside alone, or differential of the outside, leave the inside alone, and then times what's the differential of x? dx. Okay? So there's the differential equation that comes from this. Here it is for this and this. Okay? What about this one? And why does that make sense if you were to look at the graph? Yeah, because if we've got y equals 3, no matter what the change in x is, what's the change in y? Always going to be 0. Okay? And then let's look at the last one. This would be dy. Whoops. dy equals derivative of sine, cosine, leave the inside alone, and then times the differential of the inside. That's going to be 4 dx. So if we were to clean this up just a little bit, we'd have 4 cosine 4x dx. Okay. And notice, because these were both lines, the differential of y depends only on what the differential of x is. Here it depends on x and dx because it depends on where you are on the curve. Depends on the steepness of the curve. Same thing with this one. And here it doesn't matter where you are on the curve. It doesn't depend on dx or x because the differential of y, the change in y, is always 0. Okay? Any questions there? Okay. So that's how you find differentials. And we can actually use differentials to kind of explore the consistency of the chain rule. So if I were to go through and I were to find the derivative here, let's say I wanted to find dy dx, but I wanted to do it using differentials. Okay? And we've shown how uniform we apply these several times. So let's say we do this using differentials. So this would be 2x dx. This would be 2y dy. And what's the differential of a constant? 0. Well, and then what if I wanted to come back after the fact and say, well, I want dy dx. I want to differentiate everything with respect to dx. Divide both sides by dx. What happens here? Cancel out, get a 2x, just like we did when we were finding the implicit derivative. What we get here is 2y dy dx equals 0, and then of course we'd solve that. So you could approach this using differentials, and the cool part about this is, if I look at this problem right here, and let's say we wanted to find the related rates, and let's say we were differentiating with respect to time. Well, the differentials are still the same as they used to be. Whoops. Leave that off. Get in the habit there. What if I did want to find the derivative of these quantities with respect to time? What would I go through and divide by? dt. So this would be 2x, whoops, 2x dx dt plus 2y dy dt equals 0. Okay, that would be kind of like the ladder problem that we dealt with. Okay, so can you kind of see how these are related? Okay, any questions? Okay, so here's the formal definition of what a differential is. Okay, if y equals f of x, that's a differentiable function. Then a small change in x, okay, a little variation in the x direction, is denoted by dx, okay, meaning the difference in the x. Okay, a corresponding change in y, so the actual change in y can be approximated, and that's why I've underlined it here, okay, by the differential of y, which is dy. And it's given by this equation right here. So dy would equal f prime of x times dx. And we'll talk more about that in just a second, but we want to point out a couple of things about differentials. Okay, dx is independent. Okay, we've got control over that. dy is dependent. It's going to be determined by the derivative at that particular point and whatever dx is, whatever the difference in x is. So its value, the difference in y, is going to be determined by these two things: derivative and what the difference in x is. Okay, and this is something that we've talked about before, but now we're ready to deal with it a little bit more formally. Okay, if you think of dy over dx as a fraction, okay, those really aren't two separate quantities, they're tied. Okay, if we think of them as differentials, we can think of dy as the difference in y, dx as the difference in x, and if we can find a limit as dx approaches 0, as that denominator gets smaller and smaller and smaller, geometrically, the difference in the x coordinates gets smaller and smaller and smaller. If that limit exists, then that ratio is equal to the derivative. So they are the same thing as long as they're equal to each other in the limit. Okay, and you'll see why in just a second that, I mean, if we just think of dy over dx, okay, that it's not really the derivative unless that limit exists. Okay, differentials are useful when we're estimating. Okay, there are lots of other uses, but that's one of the main uses. Okay, finding differentials is similar to implicit differentiation. Okay, kind of like we showed up above. We just don't differentiate with respect to any particular variable. We came in after the fact and divided by dx and dt in those cases. Okay, okay, and dx is the actual change in x, but dy approximates the change in y. Okay? And this really is why those two things, dy dx, or the ratio of dy over dx, is not exactly the same as the derivative unless that limit exists. Okay? So I do want to show you where this formula comes from. Okay? And let's just put all these ideas together. What if I were to differentiate this implicitly? So if I wanted to find the differential of y, that is dy, and it would be equal to, well, think of this as a composite. I'd need to find the derivative of the outside function. What's the outside function? F. Derivative of the outside, leave the inside alone, then times it by the differential of the inside. What's the differential of the inside? Dx. Okay? That is where that formula comes from. Okay? Yeah. Yep. It's finding the derivative of whatever the outside function is. Yep. So if you've got y equals a function of x, then you literally find the derivative of the outside, leave that x alone, and then you take whatever that function is, or whatever that derivative is, put it in parentheses, and multiply it by dx. Okay, and we'll do a couple of examples here. Okay, So what I'd like to do before we do a few of those examples, and a couple of them are kind of interesting. We've got some pretty wild looking graphs here, okay, especially this one here, is let's take a look at how these quantities are related, okay? So we want to look at how dx, dy, delta x, and delta y are related. So this right here, this quantity right here, that distance from here to here is dx. That is the differential of x. That is the difference in x. And you'll notice that if we were to trace this down here, that is the actual difference in the x coordinates as we go from here to here. Okay, and see how this looks kind of familiar, except for we used to use x plus h. Okay. This right here is dy, and it's derived from the slope of the curve at this particular point and whatever dx is. So based on the slope and based on how far I'm going over this direction, I figure out what dy is. So if I were to go a little bit less, if dx was just this little blue line right here, that line would be dy. So this is dx, this is dy. If I'm just looking at this dx, this is dy. So it's going to change, dy is going to change based on whatever the slope is and however big dx is. Okay? How does that relate with delta y? Okay? These two are actual. This one is actual. And you see the difference between the relationship between dx and delta x and dy and delta y? These two are exactly the same. They are both actual differences in x. But what's the difference between dy and delta y? Are they the same? They're not the same. Okay? This is just an approximation for whatever the actual difference in y is. Okay? We're estimating that we're going up this far when in actuality we went up this far. Okay? But notice what happens. If I use a smaller dx, I get a smaller dy, but look at how much better an approximation that is. Okay? So dx is the same as delta x. dy is an approximation for delta y. Okay? So dy is an approximation for delta y. Okay? Delta y would be the actual change in the function values. Okay? And if we're using an approximation, okay, it's important to know how good the approximation is. Okay? In other words, how close is dy to delta y? So let's think about that. There are a couple things that it would depend on. Okay? It depends on the slope. Okay? So the larger f prime is, the bigger the slope is, the more sensitive the approximation is for the same dx. So let me show you what that looks like. Let's say I've got a curve that does this. So let me make it a little bit like this. Okay. Let's say that I use a delta x that's about this big, and to my eyeball it looks like we'd have a delta y that's like that big. Okay, let me blow this up just a little bit. If this is delta x, and this, or sorry, dx, this would be dy. Very small slope. Okay, dx is this big, very small dy. Okay, what if I change this and now I've got delta x right here? I'm going to try and make that about the same length. Look how big dy would be. This is roughly the same size dx, and look how big dy is. So for the exact same change in x, I get a tiny change in y here because it's a very small slope, and I get a very large change here in the function values and in the approximation for the function values because it's so steep. Okay? And then the second point is this. The further you go from the center of the approximation, the worse the approximation is. So let me come back and let me erase this guy right here. let's say that I was using this line as an approximation. It's a good approximation right here. Like if I stay from, say, here to here, it's a pretty good approximation. What if I go all the way out here? That would be my dy, and look how big delta y would be. So the closer I stay to the center of the approximation, the better the approximation is, as a general rule. Okay? Can anybody think of some exceptions to that? What if we did something like this? And what if I found a linearization? What if I approximated the curve right here? Okay, is it a good approximation right around here? Right around here? I think it's okay. Is it a good approximation right here? No, but then it gets better again. In fact, it's perfect at each one of these places where it actually equals the function value. It doesn't happen very often. I wouldn't worry about that too much. I'd worry about the general ideas. Okay, so the general idea is if we're using a linearization, okay, if we're using a tangent line or differentials to approximate values, the closer we are to the center of the approximation, the more accurate we're going to be, generally speaking, and the smaller the slope is, the more accurate we're going to be, or the more leeway we have. Okay, if we've got a really steep slope, you can't go very far before we get quite a bit of distortion and an inaccurate approximation. Okay? Any questions? Okay, so let's run through these last couple of examples. It says find a formula for the differential of the following functions. So it's literally this easy. This is dy. Derivative of the outside, leave the inside alone, times the derivative of the inside, or the differential of the inside. So that would be dx. That's it. This one's a little worse. So dy is equal to, what rule do I need to use here? Product rule. So we're going to do the first times the differential of the second. So that's going to be cosine theta squared 2 theta d theta. There's the first, there's the differential of the second, plus the second sine theta squared times the differential of the first. Well, that's going to be 3 theta squared d theta. So there's the second differential of the first. So let's write this down. Let's clean this up just a little bit. I'm going to write the d thetas on the end. Can I factor anything out? Okay, I've got a theta cubed here and a theta, so maybe I ought to write this. Let's write this as 4 theta to the fourth. Sorry, that's a 2 theta to the fourth, right? Cosine theta squared d theta, and then this one is 3 theta squared sine theta squared d theta. So dy would be, let's write a theta squared, 2 theta squared cosine theta squared plus 3 sine theta squared d theta. That's cleaned up a little bit. Any questions? Yeah.
Why was the d theta on the end?
Just for uniformity's sake, because that's how it's normally written. We normally write the differential on the very end of whatever the derivative is. Okay. Good? Okay. You're going to need your calculators for this, at least a little bit. Hopefully this is mildly impressive. Okay. It says calculate dy for the given values and then sketch the graph and draw line segments to represent dy and dx. So this is y equals x cubed. So we want to find dy. Dy would be based on 3x squared and whatever dx is. So it depends on, the difference in y depends on x and it depends on dx. So let's figure out what it is here. This is 3 squared, and this is 0.1. Throw that in your calculator if you would, please. Yeah. Oh, I'm sorry. Did that not show up? Yeah, that should be x equals, or yeah, x equals 3. Yep, sorry about that. I'll have to fix that in the notes. What do you get? 2.7. In fact, you don't even need a calculator for this because this would be 27 times 0.1. Move the decimal one place, you get 2.7. Okay, now, on the curve, this is the cubing function, right? So I'm going to exaggerate this just a little bit. This point right here is 3. This function value is 27. What we're saying using the differential is, if you let the differential of x be 0.1, so if you let the actual difference in x be 0.1, then we can estimate the change in the function value as 2.7. So if the function value used to be 2.7, what are we estimating for right here? 29.7. That would be our estimate for 3.1 cubed. What is 3.1 cubed? Throw that in your calculator. Okay, so here was the estimate for how much it changed. So this is what we'd estimate for the function value, and this is the actual function value. How much are we off? That's the error. Okay, so if we move over 0.1, our estimate is we're gonna have a change in function value, our dy, difference in y values, of 2.7. So if you're at 27 and you go up 2.7, you're going to get to 29.7. Does that make sense?
Yeah.
That's pretty darn good, isn't it? Okay, using differentials, we're within 9 hundredths, 91 thousandths. Pretty darn good. Okay, let's take a look at this last one, and we need this guy right here. So I want to know what dy is. If theta is 0, big favor there, right? Okay, and d theta is 0.05. So this is going to be 0 squared, and then all of this is a 0. So that's a 0, that's a 0, and this is negative. Right here. I'm just plugging into this one. I plugged in a 0 here. Okay, and then this is negative 0.5. Okay, so what is the estimate for the difference in y? Okay, we estimate a difference in y of 0. Okay, now let's see. Do you know what that looks like? Okay, it's going to be a sine function, and let's see. It's going to wiggle back and forth a lot the larger number we plug in. And its amplitude is determined by theta cubed. So it's going to do something like this. It's going to oscillate more the larger number we plug in. And because the amplitude is determined by whatever the number is in front, and we cube that. So if I plug in a 0, I get 0. If I plug in a 1, I get positive 1. If I plug in a negative 1, I get negative 1. So it's gonna do something like this. Okay. Just estimating, of course. Okay. So let's throw that in the calculator and take a look at it. So this is, I'm going to type in x cubed and then sine of x squared, close the parentheses. I'm going to get rid of this right here. No, it's a 0. I'm plugging in a 0 for theta. We already plugged it in. Okay, what does it look like the slope is there? 0. Is the derivative supposed to be 0? Yes, it is. So what's our estimate for the change? 0. Okay, so if we were to draw this, it's going to look something like this. Okay, so I'm just drawing this little bit right there. Okay, and if we were to draw in our dx's, it says negative 0.5, so we would have gone back 0.5, and what's our estimate for the change? Okay, so it didn't go up or down. So there's our dx. We have 0 for dy. Okay, now let's type that into the calculator. Let's see what we actually get. We estimate, okay, first of all, if you plug in a 0, what do you get out of this? The original function, 0. Okay, so the original function value is 0, and we're guessing that we're going to have a change of 0. So we're guessing our new function value is going to be 0. Pretty easy, right? Let's type this in, and I'm going to grab the home screen, and I'm going to do negative 0.5 cubed, and then sine of negative 0.5 squared, close the parentheses. Pretty close. Okay. Weird problem. Okay. Let's see, and then last little bit, and I'll let you go early next time. So it says, can you tell which approximation in A or B, which one's more accurate? Just by looking at the information here. So this one is centered at 3, and we only go 1/10. This one is centered at 0, and we go 5/10. Okay, normally the further you go, the less accurate it is, right? Okay. You can't really tell on this one. This one, because the slope is 0, usually you're not going to be able to tell in comparing functions. You'd actually have to go through and make some numeric comparisons. But generally speaking, the closer we are to the center of the approximation, the better off we are, the more accurate we are. And the shallower the slope is, the smaller the derivative is, the better off we are. Okay? So this one had a really shallow derivative. I mean, it was 0. Okay? Here we had a pretty large derivative. The derivative there was, the slope there was 27. Okay? So pretty large slope. Okay, and then the last thing I want to mention is you've got some problems on your assignment 23 through 28 where they just say, find an approximation for this. And that's all the instruction they give you. Okay? What you're going to need for those is you're going to need to figure out what function you ought to use. So on this one, what function should we use? Use x to the 4th. And you're going to need to use a center of approximation. So if you had to choose something that's easy and close, what would you use? Use 2. Okay? That's all. Yep, just like we did there. Okay? Any questions? Talking about these most of the time is harder than actually doing them. I think you'll find them relatively easy. Okay? We'll finish up the chapter tomorrow. We're going to do some interesting and wild functions. And that'll be it. Remember, review Monday, test Tuesday, and Wednesday. Make sure you've downloaded those reviews, that you've looked at those so you can come and ask questions on those.